Good day, and welcome to our webcast, Evaluating Noise in Electric Motors, brought to you by CFE Media and Technology and sponsored by Grundfos, Lenza, and SCW Eurodrive. We're joined today by Tom Bishop, an EASA Senior Technical Support Specialist. I'm Kevin Parker, an editor with CFE Media. Today's presentation can provide continuing education credits. CFE Media has met the standards and requirements of the Registered Continuing Education Program. Credit earned on completion of this program will be reported to RECEP at recep.net. Determining the source of noise in a motor is often more challenging than correcting it. However, a methodical approach to investigating the noise can narrow down the possible causes and therefore make it easier to resolve the noise issue. In this session, we will address the causes and characteristics of the primary sources of noise in AC motors. Learning objectives today include possible sources of noise in a motor, how to investigate motor noise, the nature of motor noise, mechanical noise, and windage noise, and how to reduce or eliminate noise intensity. This event is a live educational webcast presented on December 14th, 2021. The educational category is Technical Health and Safety. Here are some tips to help you get the most from today's webcast. If you experience issues with the slides or audio, refresh your browser or click the Refresh Media button under the presenter's picture. Control the volume of this webcast by adjusting the volume on your computer or on the webcast platform. For technical problems with the audio or slides, click on the question mark at the top right-hand corner of the screen to access a list of system checks to try before contacting an online technician. If you do need a technician, type a message in the Ask a Question box and someone will get to you as quickly as possible. The Ask a Question box is also used to ask the speaker questions. The live Q&A session begins after the presentation concludes. Today's webcast is being recorded. You will receive an email within a week with a link to the on-demand event. To take the Learning Unit exam, use the Learning Unit exam tab option at the top of the screen. The exam will open in a separate browser window. You can complete the exam after the webcast. However, the link will break when the webcast signs off. We'd now like to share with you some brief videos from today's webcast sponsors.
Getting stressed out by how complex automation can be? Lean on the experts from SCW Eurodrive and check out our MoviKit automation modules. MoviKit is a collection of pre-built software modules for many common motion control applications ranging from simple drive functions like speed control and positioning all the way to complex functions like camming and even kinematic robot control. MoviKit makes it easy for engineers of all skill levels to do their own automation. We handle the complex programming part, and you simply enter your parameters and go. Shorten your startup time with configurable automation and motion control functions. No need to waste your valuable time with complex automation programming. Check out MoviKit, the pre-built software modules from SCW Eurodrive.
Welcome back. I'd now like to introduce today's speaker. Tom Bishop is a Senior Technical Support Specialist with the Electrical Apparatus Service Association, otherwise known as EASA. Bishop joined the EASA staff in 2002 with more than 30 years of hands-on and engineering experience at electrical machinery, manufacturing, and apparatus service firms. He has a BS in electrical engineering and is a licensed professional engineer. Tom has authored dozens of technical articles and papers and presented numerous seminars on electrical motor application, maintenance, and repair. In addition, he is chairman of the EASA's Technical Services Committee, a principal member of the National Fire Protection Association, Electrical Equipment Maintenance Committee, NFPA 70B, and a life member of the Institute of Electrical and Electronics Engineers. Tom, welcome to today's webcast, and please go ahead.
Thank you, Kevin, and welcome to everyone. We'll get right into our session on evaluating noise in electric motors. Cover the introductory material here. We've got three primary sources of motor noise. It can be magnetic, mechanical, or it can be due to windage. And during this session, we're going to discuss the causes and characteristics of each of those three sources, as well as providing guidance for reducing or eliminating the noise associated with them. And the scope, the motors that we're going to be discussing, the noise we're talking about will be squirrel cage AC induction motors. Magnetic noise is sometimes termed electromagnetic noise or electrical noise. It's the result of mechanical forces that are electrical in nature, meaning that it's a pressure, it's like a push-pull or an attraction and repulsion of the different parts of the electric machine against each other, especially things like the thin metal discs that make up the stator laminations where the windings go in the motor. So we've got all that series of stacked discs, and magnetic noise is when those discs can be moving against each other, one against the other, could even vibrate some of the wires in the winding. That's our push-pulling or attraction and repulsion due to the alternating magnetic field. That's our alternating current, where we have through each cycle, we've got a positive half of a cycle and a negative half of a cycle. And as a result of this, we can get what's called twice line frequency hum. So if our line frequency, typical here in North America, is 60 hertz, that's 60 cycles per second, twice line frequency would be 120 hertz, 120 cycles per second. And that type of hum, a common type of apparatus that we hear that type of noise from all the time is a transformer. The magnetic noise in itself, as part of the motors we're talking about, and a noise source, it's typically the second highest source for 2- and 4-pole motors, with windage being the first for those higher speed machines. Higher speed, what I mean by that is that a 2-pole motor, the synchronous speed, the magnetic field revolves at 3,600 revolutions per minute or cycles per minute. 4-pole would be 1,800. It goes in proportion. There's always a north and a south, so we always have even number of poles, pole pairs. So 2-pole, 3,600, 4-pole, 1,800. Slower machines, 6-pole, 1,200. It goes on like that. So that's our higher speed machines. We tend to find more occurrences of magnetic noise being troublesome, and with windage being probably the most troublesome. And as we go down in lower speed machines, the magnetic noise starts to become the dominant source. And the reason for that, if we look at these graphics, disregard the numbers, they're just for, it's taken from a manufacturer's dimension sheet. But the 2-pole, if we look in this area, we've got these lines, that's the slots where the windings go in. Behind that, between that and the outside of that core, that's what we call the back iron or below slot iron. And we see a relatively thick, dimension there, a large dimension. We go to the lower figure for a 6-pole, slower speed machine. We've got the slot space, and then the space between the slot and the outside of the core, its back iron proportionally is much smaller than what we see on the 2-pole machine. And because this is much smaller, this core is more prone to deviation, or variation, flexing, distortion, and so forth, the magnetic field can affect it much more than what we would see in the stiffer two-pole machine. If that main source for the noise is magnetic, then what we also find is that the overall noise increases when we apply load to the motor. So at lower levels of load or no load, we've got one level of noise, and as we increase the load, the noise level starts to increase. Also, just as a sidebar comment, the noise level, if the source is magnetic and we de-energize the motor, in other words, we take away that electrical source, the noise instantly goes away. So magnetic noise, a characteristic of it is that when we de-energize the motor, the noise instantly goes away. So we've got this noise, it does increase. The amount that it increases with is smaller for a 2 or a 4-pole motor, and much greater for motors with 6 or more poles. And this is illustrated in this table that comes from IEC. It's the International Electrotechnical Commission. It's an international standard, 60034-9, which is related to noise and rotating electrical machines. And we see we've got rated output power here, and disregarding in a sense the numbers, but just noticing that we go from 1 to 2200 and over, that we've got the lower power ratings towards the top, higher power ratings towards the bottom. And now if we look at 2-pole, 4-pole, 6-pole, 8-pole, as we go across from right to left, the 2-pole, just a nominal change, about 2 dBA, 2 decibels. And as we go to lower and lower speeds, higher count of poles, take this one here, 11 kW to 37 kW, we go from 2 up to 7 when we're at 8-pole. And to explain what we have in these, in North American terms, we go by horsepower. So 1 kW is a little bit over 1 horsepower, 11 kW is 15 horsepower, 37 kW is 50 horsepower, 110 kW is 150 horsepower, 400 kW is a little over 500 horsepower, and 2200 kW is about 3,000 horsepower. So it covers, the full range from basically any integral horsepower type motor on up to, an unlimited size. But point being that, especially in the smaller kW ratings, much greater increases in noise than what we see in the higher power ratings. But still, for the slower speeds, we have more change in noise sound level from no load to full load. The design of the motor and its impact on noise. So the motor designer is planning to create a motor, and some of their considerations that reflect back on noise. If we use the largest possible air gap, that can reduce magnetic noise. But if we use a larger air gap, what happens is we're driving that magnetic field, magnetic flux, the lines of magnetic intensity through that air gap, that airspace. The bigger the space, the more energy it's going to take. What it's related to is the amps, the current that the motor's going to draw. It's going to draw more current at no load and with load because the air gap is larger. And because of that, the power factor with higher amps for the same amount of power, we've got a lower power factor. Also at no load, we're going to have higher no load current. So those are potential drawbacks there, especially if the utility is going to impose a power factor penalty. So a way around this, what can the designer do? They could use a longer core to decrease the air gap flux density. In other words, let's say, if the design called for a 10-inch core and they had to reduce, had to use too large of an air gap, maybe they'll go to an 11-inch core with a smaller air gap and lower air gap flux density. With reducing the flux density, the forces, the mechanical forces trying to pull the stator and rotor into each other vary by the square of that air gap flux. So if we reduce the flux density 10%, let's say we're at 0.9 of what we were, 0.9 times 0.9 square, 0.81, we've reduced the forces inside that motor by about 20%, and that's going to significantly decrease the noise. And it also usually improves the power factor, so it's a double benefit. The drawback, a longer core, material-wise from the motor manufacturer. If I need 10% more material, it's going to cost me, in other words, the overall cost of the motor, maybe it's not 10% more, but it's a significant increase in cost because of the material that's been added. And now maybe I can no longer be competitive with that motor against, other motor manufacturers. So that's the downside or the drawback, that the longer core, great idea, but it costs money to do that. So that's our trade-off. So that's the challenges for the motor designer, are to come up with something that uses the largest possible air gap with really the shortest possible core. Slip noise relates to the difference in speed between the operating speed of the motor and either synchronous speed of the motor or line frequency relationships. That if we've got a motor that's synchronous speed 4-pole 1800 RPM and its full load speed is 1740 RPM, 1740 from 1800 is 60 cycles per minute, or 1 cycle per second, which is 1 hertz. That would be our slip noise. We'd have a slip noise. The frequency of the slip noise is what we call a beat frequency, and that beat frequency is typically twice the slip frequency. So if we had 1 hertz slip, 60 CPM, we're going to get 2 hertz, twice that, for our slip noise. And because it is low frequency, it's going to tend to what I would call come and go over a noticeable period of time. That this coming and going, this kind of constantly changing, gradually back and forth, is more annoying to a lot of people than it would be if it was something like the transformer type hum, the twice front line frequency noise. So that can make it an objectionable noise source, even if it's not very great in amplitude. Other things that can cause this, open rotor bar or an end ring that's fractured could also produce slip noise. But again, it goes back to slip noise in itself is an inherent part of the motor, simply because it's going to have slip, and the lower the speed, the lower the load, the lower the slip frequency is going to be, the more noticeable, but it's more objectionable as that frequency starts to increase. Skewing. What is skewing? What do we mean by skew? If we look at the picture here, we see this is the stator, and this is where the laminations are, those discs with holes in them that the winding coils are embedded into. And here we have the rotor, and we see if we look at this, well, let's go back, look at the stator. We've got lines that are basically parallel to the periphery of the frame. These lines going across, that's the outline of the rotor bars. And instead of going in parallel to the shaft center line, they're at an angle to the shaft center line. That's what we call skew. And that skew, it's an intended angle. What it does, because it's at an angle, these lines don't line up with any of the lines inside the stator. So since they're not connecting directly to each other, that reduces some of the interaction between them. And the benefit of it is that it'll reduce electrical noise. Other things that are not noise related, it'll also help with starting torque. So that's a positive thing. But this reduction in noise is what we're interested in here. And when the designer tries to figure out, well, how much of an angle do we need in this particular motor, what they'll usually do, there's no set rule on what value is the correct value or what works best. But generally speaking, it's between what we call 1 stator slot distance and 1 rotor slot distance, usually whichever results in the larger number. So if we had a 48 slot stator and a 30 slot rotor, with 30 slots, the space between the rotor bars is larger. The skew would probably be about 1 rotor bar from one end to the other. Air gap. The air gap, when we've got the rotor centered in the stator, the ideal condition is that the rotor is perfectly centered within the stator bore. If there's any variation between one side of the rotor and the other as far as the bore, the air gap between them, let's say we had an average clearance around that bore of an air gap of 50 thousandths, And now we find that the air gap is offset, the rotor's offset. Instead of 50 thousandths on one side and 50 on the other, we find that maybe it's 75 on one side and 25 on the other. 3-to-1 ratio. If we're off eccentricity by about a third, we can see here we're up around 5 or 6 decibels, as opposed to if we're down around 10% variation, we're less than 1 decibel. And the reason I picked 10% is that for most motors, at least 4-pole or slower, we allow for a variation. We try to keep it within 10% so that the noise change and the unbalanced magnetic pull is kept well within bounds. And as with the air gap magnetic flux density, unbalanced magnetic pull follows along with that, that if we had an unbalanced magnetic pull, if we were off by 30%, it's the 30% times 30%. It's a much larger effect on magnetic pull. If we had put it in better perspective, let's say we had a unit of 1 over here on one side of the rotor and a unit of 3 on the other side of the rotor, that 3-to-1 ratio, it's 3 squared. The force on the side which only has 1 unit of clearance is 9 times the force that we have on the side with 3 times the clearance. So that's why it's such a hazard, a risk. Not only does it increase electrical noise, but it also increases the risk of the rotor making physical contact with the stator. Things that cause the air gap to become unequal. We could have an eccentric rotor. In other words, the rotor, we put the rotor on the shaft, the rotor core should be a circle, and its dead center should lie within the center of the shaft. If it's offset, it becomes somewhat like an egg shape or a cam action, like a camshaft. It's offset, it becomes eccentric every time it goes around. The air gap, if we looked at the air gap in one place relative to the stator, it would constantly change because of rotor eccentricity. Similarly, we could have the stator bore being eccentric, or what we might call egg-shaped. And now the rotor, when it's spinning, even if the rotor's dead center, it still has more air gap on one side of the stator than another side of the stator because the stator bore is not concentric all the way around. A bent shaft, if the rotor shaft, the shaft supporting the rotor is bent, the rotor follows that bend, and now it kind of sweeps around, and we've got a bow in the rotor that moves around. We have a constantly changing air gap, so we've got that unbalanced magnetic force constantly changing, trying to vibrate the motor, and also induces some electrical currents that vary, as well as the greater it is, the more the electrical noise that we hear from that machine. Shaft journals could be machined out of concentricity, which, going back to an eccentric rotor, that may be why, even though the rotor is concentric to the shaft that it's mounted on, the shaft that it's mounted on is not concentric to the shaft journals, therefore the rotor becomes eccentric. And with the stator, if the housings weren't bored concentric to the frame, then what happens is now we've got the rotor being supported either too high or too low or to one side. We've got eccentricity there. We could also have an end bracket to stator fit that's not concentric. We might have a good fit at maybe the drive end, for example, but a not good fit on the opposite drive end. So now what we have is we may have a concentric bore at one end and an eccentric bore at the other end, leading to all kinds of issues as far as mechanically, and again, in terms of the electrical noise that we get from that machine. A frame that's distorted, that's going to twist, and it's going to change the air gap to varying amounts throughout the bore from one end to the other. Again, a contributor to electrical noise. Mechanical noise, moving over from magnetic into mechanical issues. Strictly speaking, all noise is mechanical in origin, that the noise that we hear, even with a magnetic source, the magnetic source comes out to what we hear with our ears as a mechanical, something mechanically gets us, let's call it, excited by it, changes by it. And that's related to pressure waves being transmitted through air or any other fluid, gas, liquids, and solid material. So we've got sound moving through all the different materials. It could be the air flowing through the motor. Not usually liquids in motors to a great degree, sometimes oil for oil lubricated machines, but solid materials, the winding, the laminations, the rotor with its bars and end rings, and so forth, bearings even, the shaft. All these materials are carrying the noise through from inside the motor externally to where we hear them as a mechanical sound. And it's produced when these magnetic materials are attracted and repelled from each other. So we still have a magnetic source from this alternating magnetic field, but we're getting mechanical sounds. Maybe the electrical source excites something like an air deflector. The frequencies that we hear, the range of human hearing, go from about 20 hertz to about 20 kilohertz. So the higher the frequency, usually the more objectionable they are to the human ear. But that's our range for mechanical noise. And an example of mechanical noise from a loose stator core, where the stator, those laminations, the thin discs that hold the windings in, go inside of a frame. The example here is a rolled steel frame. So you have something that's like a steel shell. It's kind of like a big can, if you will. And the core is in there and it's not tight. The noise, we'd characterize it as a buzzing sound. And a way that we can confirm that this sound is being induced by a loose fit of the stator core in that frame is taking what we call something like a dead blow mallet and tapping on the outside of the frame, the shell of the motor, while the motor's running. And if that tapping, if the noise from the motor changes while we're tapping, that's an indication that the stator core is loose within that rolled steel frame. And at times, we might even be able to get that noise level to cease. So that's, a potential corrective measure would be to tap on it with the dead blow mallet and be able to reduce the noise to the point where it's either acceptably low or possibly even goes away. That said, over time, it may come back again because we have to bear in mind that the inherent root cause is that that stator core is loose in the frame and it could loosen up again over time. A physical rub can generate noise. We have examples here. We've got damaged or worn bearings. So how do we correct that? Simple approach, replace the noisy bearing. If we have fan contact, external fan contact with the cover or an internal fan contacting with an air deflector, what we want to do there is ensure that the fans are properly located. In other words, move them away from making physical contact with a cover or an air deflector. Relocate the fans. Also, rotor contact with stator. Make sure that the rotor stator concentricity is within tolerance, within that plus or minus 10% from the average. And if there has been physical contact, in all probability, if the rotor has made contact with the stator, the motor would need to be dismantled and some repair work done so that this can all be corrected, because probably what's also happened is either the shaft is bent or the bearings are destroyed. So it would involve more intensive repair work, but that's the noise from rubbing. Again, that's kind of the, I don't want to call it worst case, but this is certainly more challenging to deal with a stator rotor contact than it would be from just noisy bearings or fans that are contacting an air deflector or a cover. Bearing noise, excessive noise from the bearings can be caused by things like non-uniform balls or rollers, where the balls or rollers are no longer, true spherical shapes. There's some, out of roundness to them, or they've got indentations in them, or they've been scuffed up, poor surface finish, leading to, degradation there. So that gives us noise from the bearings. Essentially, when we have these conditions, non-uniform balls or rollers, or poor surface finish, the bearing is already in a failure mode that we're not going to be able to correct for this by doing something like cleaning the lubricant, flushing it out. The bearings with that kind of noise level need to be replaced. If we've got something like ball or roller retainer rattle, that we might be able to correct by putting grease into the bearing, and now it quiets it down. The key to this as to whether or not the rattle is going to go away is whether or not it stays away. That if we grease it and the noise goes away and we don't hear it again, for months on end, then fine. But if we do it and we grease it and the noise comes back, then that indicates that there's more than just retainer rattle. We probably also have some degradation to something like the balls or rollers, and the bearing's going to need to be replaced. Eccentricity, maybe we have something like the inner race of the bearing, the journal, is out of round. It's eccentric, which makes the inner race of the bearing eccentric. And now, as that inner race rotates around, we've got a space between the inner race and the outer race that's basically filled by the balls or the rollers. And as we rotate that machine, as it goes around, if we've got that eccentricity where it's got the high point, when it's at the high point, we're literally squeezing the balls between the inner and outer race, and eventually that's going to do degradation damage to the inner race of the bearing and to the outer race where that eccentricity occurs. When we get past that point of tightness, then it's relieved itself. We don't get the wearing pattern there, but we get that wearing pattern because of the eccentricity of the journal. And that, going back to, well, what caused the eccentricity, not just noise, what caused the eccentricity? Maybe it was an out-of-round journal or just a burr, just a piece of, material, metal, contaminant got caught between the inner race of the bearing and the shaft journal, causing the eccentricity. Rubbing, we might have something like an inner cap on a bearing that comes in too far, too close to the bearing, and starts rubbing up against the inner race of the bearing, or maybe it makes contact with the cage that holds the balls or rollers in place. So that rubbing results in bearing noise. The bearing noise, the result is that it's impact noise or resonance excitation. What we're doing, the bearing noise, what it goes beyond the bearing is it excites something else. That thing about the noise traveling through other parts, through the air, especially through metal, and now we get this noise that impacts on bearing housings and air deflectors or any other part that's efficient at radiating noise, that we create a resonant condition. And one of the things that's particularly prone to this is things like air deflectors, because many times they're just a piece of stamped sheet steel, so they lend themselves to becoming a noise source. They're almost like a musical instrument sometimes. Identifying the bearing noise. Some things that can cause the noise. If we have what's called brinelling, we get a low-pitched sound. Maybe get kind of like a rumble or something. Brinelling. Brinelling is impact damage on a bearing that results from the hard contact of the balls or rollers against the raceway. Brinelling, it's a sharp indentation into the bearing. It's kind of like if we took a motor example, if we took a motor and we dropped it and the balls indented into the raceway, those indentation marks are called Brinell marks. So that's that kind of an indentation mark. It doesn't have to be that pronounced, but that's what we call Brinelling, low-pitched noise. There might be dirt in the bearings, some contaminant that gets in the grease and into the bearings, the rollers, the balls, the raceway, and so forth. Gives us a shrill or kind of like a shrieking sound. Very objectionable, harsh on your ears. It's the kind of noise you just don't want to hear that. If you had that, you'd probably almost want to shut that motor right down. So that's dirt in the bearings can do that. We might get an intermittent crackle sound. And that can be due to the grease that's being used. It might have to do with the grease viscosity. It might also have to do with how much grease is in the bearing. Maybe we have too much grease in the bearing, and now what's happening is it's not giving us a smooth lubrication process. How do we reduce bearing noise? There's a simple way that the manufacturer, we go back towards design of the motor. The manufacturer, when they're doing the design, they say, okay, what can we do to reduce the noise in this bearing assembly, in this motor? We need to do this before. We don't want to build the motor and find out it's noisy. If we're building 1 million motors a year, we want to have something that's part of our process that says we're not going to get bearing noise from these motors, or at least reduce the possibility. And a good way to do that is to use what we call a wavy spring or wave washer to actually preload the bearings. So what that does, and I'll go to the next slide, we look at this. We see here's this wavy washer, and again, just jumping back. So it's got, it's flexible, it's bendable, so it can be compressed. It preloads the bearing, and The way it's doing it's up against the outer race of the bearing. The end of the motor, if you look at it here, this is a totally enclosed fan-cooled motor. We're at the opposite drive end. Normally on a motor, most common, we find that the drive end bearing is locked. The outer race is locked, the inner race is locked, it's fixed. This bearing at this end and the shaft, they're free to move so that when the motor heats up, the shaft gets hotter and expands more than the rest of the frame. So this bearing assembly, this bearing is going to get pushed towards the fan. So as that expansion occurs, we need a place for the bearing to be able to expand, and that wave washer is filling in part of, not all of, just part of that space, so that when the motor shaft expands, it starts preloading. The wave washer preload force acts against the bearing, and what it's doing is it causes each ball to follow the same path on each bearing. And that's another benefit of this arrangement, is that not only does it preload the opposite drive end bearing out here, it also preloads the drive end bearing because it's pushing the bearings against each other axially. And now the bearings, everything being concentric, the bearings are going to ride, the balls or rollers are going to ride the same race all the way around every time because of that preload from it. So that preloading decreases the noise due to the balls rattling. In other words, they're not stable, and it decreases the high frequency vibration that would have occurred if the bearings weren't stable that way. And it can improve dynamic balance by removing some bearing looseness, that we've got the bearings preloaded against each other. They're not slopping, moving back and forth against each other. If it was something like a vertical motor, some type of preloading, maybe not a wave washer, but some type of spring loading on the bearings can help preload the bearings, even a thrust load, intended thrust load. It improves dynamic balance by removing the bearing looseness and allowing the bearing to ride in the center. It keeps the bearing, it keeps the rotor centered in the air gap. If we have too much bearing preload, it's, if one wavy washer is good, would two wavy washers be better? The answer is no. If we have too much preload, that can produce, instead of a high frequency vibration, we're going to get a low frequency noise. And because the preload is too great, we can overheat the bearings. We can mechanically overload the bearings, reducing the bearing life. Friction noise is due to insufficient lubrication between two sliding surfaces. So if we don't have enough grease in the bearing, we get noise from that due to high impact vibration from the rapid intermittent contacting of surfaces. So that there's smearing or skidding as the rollers or balls are making contact with the surface. So we need that lubricant to keep everything moving smoothly. When the rolling element bearings, if they don't have enough preload, that can also lead to this sliding action. So again, that preloading helps keep the bearings, balls or rollers in uniform contact with the races as the machine rotates, as the rotor spins around. And when we have this, when we don't have good contact, we can get a sound like hissing air. So that's a characteristic there. Airborne noise, any structural part can become a source for airborne noise. And if it's excited with sufficient energy at its natural frequency, that part, again, I go back to something like an air deflector, because they're so prone to airborne noise, creating a resonant condition that sets, it sets the part into motion. It sets the air around the part into motion. How can we deal with that? Well, we can use noise deadening or damping materials to reduce that noise level, that sound level. And if it's something like, an air deflector or drip cover, some other similar component, our totally enclosed fan-cooled machine, the drip cover, the air deflector inside, whether it's totally enclosed fan-cooled or a drip-proof motor, that air deflector, a good fix for that to reduce noise, damping material to use, an RTV silicone sealant between the air deflector and the end bracket that it mounts up against, so that RTV material acts as a damper and then reduces that noise and often eliminates it. If we've got a drip cover or something like that, another way around that, we look at, can we put sound deadening material on top of that cover, around it, surround it. The sound absorbing material, the way the sound absorbing material works, first of all, if it's the denser it is, the thicker it is, the less porous. In other words, the denser it is and heavier it is, the less noise we get. So it's got more dampening qualities. Interestingly, is what's of interest is that noise, what the damping material is doing is it's taking that noise and converting it into heat. Not a lot of heat, but it just that's what it's doing. By absorbing the noise, it generates some small, a very low level of heat. But that's the sound absorbing material. So the benefit is we reduce the sound. The potential drawback, if we totally enclose the motor, encase it in a sound deadening material, the motor's going to run quiet, but not for very long because it needs cooling air to move through it. So for restricting the cooling air transfer through the machine, now what we get is much increased temperature, and then the winding and the bearing and lubricant life is significantly reduced. So we've talked about magnetic noise, we've talked about mechanical noise, and now we have windage noise, which accounts for the majority of the motor noise that we find, within motors. Most common in 2- and 4-pole motors, not quite as dominant in 6-pole and slower. As the speed goes down, windage is less and less of a factor. What is it caused by? Obstructions near rotating parts that move air and create turbulence. So anything, if the fan is too close to something, if there's some kind of something that sticks out, maybe there's a bolt or even a grease fitting that's too close to the fan, grease pipe, we get turbulence, we get noise from that. The type of noise we get is what we call broadband. An example of broadband noise would be what we call white noise. So it's a wide range of frequencies. It's not any one specific frequency in most cases. How do we reduce the windage noise? Minimize the obstructions to the cooling airflow paths. Get the fan away from being too close to something like a grease fitting or too close to the fan cover. If it's a large open enclosure motor, what we can do there is look at, for one thing, we might consider, well, if we reduce the cooling fan diameter on that motor, what will that do for the noise? It won't significantly reduce the noise. But moving up, most of the noise in our open enclosure larger motors comes from rotor bar fan action. That the rotor bars, there's vent ducts in the rotor, and those vent ducts where the air moves past the bars, that's where we get our rotor noise. So it's not from the cooling fans or the fins, but it's from the rotor bars. And that airflow can induce resonance. One way that we can correct for that, as a designer this would be, is to change the number of fan blades to reduce the noise. So that's a designer's option. Other things, large open enclosure motors, radial vent ducts through the rotor and stator can produce pure tone, not broadband, but pure tone, highly irritating, frequency typically above 1,000 hertz, often termed a siren effect. And that type of noise, the way the designer can reduce that in the design stage is to offset the number of the rotor ducts with respect to the stator duct. So we've got slots, axially speaking, we've got slots in the rotor that don't line up with the equivalent slots in the stator. They're offset from each other. So it goes through part of the air gap, it goes into the air gap, moves across the air gap a little from the rotor and then through the stator, as opposed to going straight from the rotor right on through to the stator. If it went straight through from rotor to stator, we might get this siren effect noise. By offsetting it, we get a large reduction in noise. The designer has to be able to be the one to do this, though, because we do have a reduction in airflow by virtue of the fact that we've offset those ducts from each other. On totally enclosed fan-cooled motors, external fan diameter reduction in this case is very effective at reducing noise. We said on those large open motors it wasn't, but on these it is. So we've got that fan diameter reduction, very effective at reducing noise. However, when we do that, the reduction in that diameter reduces the airflow. And if we reduce the airflow, we're going to reduce winding, lubricant, and bearing life because we're going to increase temperature. So a way to reduce fan blade frequency noise would be to increase the clearance between the fan and stationary parts, as we did with the other machines, and also the possibility, again, in design stage, using non-symmetrical spacing of fan blades. Maybe we have a fan with, let's say 12 blades. So instead of spacing the 12 blades like the hours on a clock, part of the way through it, we change them so they're no longer at hours of the clock spacing between each other. And that offset, that intentional non-symmetrical layout, helps reduce the noise. Okay, with that, we've covered the magnetic, mechanical, and windage noise sources and potential solutions. So moving on to the next part here.
Well, thanks so much, Tom, for an extremely cogent presentation. For our audience, type your questions for Tom in the Ask a Question box in the interface. We'll get to as many as time allows. Questions that we don't get to today will be posted online with the archived version of this webcast. Be sure and download a copy of the presentation using the Event Resources tab. We've got about 12 questions, so we've got a little bit of time here. Let's get started. First question, Tom, does motor noise always result in vibration?
Okay, motor noise and vibration are definitely related to each other. We can have, let me put it this way, we can have vibration without, to our ears, audible noise. And likewise, if we've got noise, even though we have noise, the level of noise is not a strong indicator of the level of vibration. So because one motor's noisier than another, or the motor's noisier now than it was before, that doesn't mean that the vibration level has increased. They're related, but they are independent of each other.
Good. Conversely, does the vibration always result in noise?
There again, if we have vibration, it's more likely that the vibration is also going to create some level of noise. If we've got a rotor that's out of balance, we're going to get kind of a rumbling sound from that motor, kind of a throbbing, or almost like a beating sound at times. So vibration, yes, it does cause noise. And as with the noise effect, more vibration, there usually is a slight increase in noise, but it's not a dramatic increase in noise.
Good. Is windage noise physically destructive?
Okay, windage noise in itself is not physically destructive. If we think about our three sources of noise, when we have mechanical and magnetic noise, that's because things are moving. Things are happening. We've got that electrical pressure, compression and decompression moving that way. With windage, what we have is we've got air moving through a machine. So the air in itself, its movement through the machine, the windage, doesn't normally damage something. Strictly speaking, the windage, not from a noise perspective, but if the wind had contaminants being carried in it, then those abrasive particles, if there were in the contaminants, that could do damage to the windings. But predominantly, the windage itself is not going to cause any physical damage to any part of the machine.
Thank you. Next question. Will a longer core also increase the overall size of the motor?
Yes, and that's another potential drawback to it, that the internal length that's available for the core, if the core needed, I mentioned like that 10%, to pick that number again, the core's 10% longer, is there enough space within that frame to make that core 10% longer and possibly, even adequately support it? And when you make the core longer, the windings go further out, and now they may become too close to the end bracket. So there's definitely limits to how much core length can be increased.
Good. Just 1 second here, I got a little bit distracted. What factory tests can confirm the eccentricity of the air gap? Or is the eccentricity associated with an installation problem? Is there a field test to get a better handle on that?
Okay. A factory test for eccentricity, if it's something like a totally enclosed fan-cooled machine, normally there aren't any access points to go in and measure with feeler gauges what the physical air gap is within a machine. on some sleeve bearing motors, especially larger sleeve bearing motors, there are provisions to be able to go in with what we call thin feeler gauges and measure the air gap at 4 locations as you go around the bore. The way the factory would know whether or not there's concentricity in that would be relying on their machining practices, that the stator rabbet fit, the housing where that housing fits, that rabbet fit is concentric to the stator bore, and that the rotor has the bearing journals, with the bearing journals as the reference, that the rotor core outside diameter runs true to the bearing journals. If we've got that, and then the end brackets, the end bracket has to have the end bracket rabbet concentricity concentric with the bearing housing bore, where the outer race of the bearing seats. So that's how they would do it that way. In terms of trying to measure any of this in the field, or after the motor's been assembled, again, if it's got access ports like a sleeve bearing machine, some sleeve bearing machines, then you can measure it. Other than that, if it's in the field, it wouldn't be something that you'd have any direct way of being able to measure that you have air gap eccentricity. The only, what I would think of, not only, but one backdoor approach would be if you measured shaft runout and you had shaft runout, the shaft being bent could be an indicator that the rotor is running eccentric inside the stator, but it's not a strong indicator. So in the field, there's really not much that can be done to check stator to rotor concentricity.
Good. Now, the question you just answered came from Dave, and the next question is also from Dave, so I have to assume the two are related. The question is, do generators have the same issues, specifically referring to a motor generator?
Okay, a generator, whether it's a DC machine, with an armature, commutator, and so forth, or an AC machine where it's got the synchronous rotor poles, the air gap eccentricity is still going to affect it, to where if we've got the air gap offset on one side, we can get unbalanced magnetic pole. Relatively speaking, if we've got more air gap on one side, less air gap on the other, the ratio of that difference between the two sides, square that ratio, and that gives us an indication of how much stronger the magnetic pole is going to be on the side that has the closer clearance.
Good. Next question comes in from Iman. And Iman, I'm going to do the best I can with this, and hopefully we'll communicate here. Sometimes we are facing a noise from a new bearing that's just been installed on a rotor shaft during assembly. This sound will be fluctuating during the solo run test of the motor. Does this require any remedy, or can we proceed to coupling the motor?
Okay, well, if you have something like any sound from bearing is probably an indicator that there is an issue in the bearing. Where I would start with that is I would maybe try and flush through some fresh lubricant. Don't just add lubricant to it, but flush whatever you add in, take some out, and see if changing the lubricant, because it could be just that either the bearing doesn't have enough lubricant or too much in one place, so you're trying to displace it. Do that and see if the noise stabilizes or goes away. If the noise doesn't go away, then I would encourage you, if you've got vibration analysis equipment like a spectrum analyzer, to do vibration analysis on the bearings at the bearing housings and analyze for bearing fault frequencies, because maybe there is something wrong with the bearing. Something's happened. Maybe there's an inner race fault, an outer race fault, something to do with the cage. So that's where vibration analysis can be very beneficial.
Good. Next question, is there a best practice for determining the type of noise being heard?
Well, the best practice, I don't know if I term it best practice, but the simplest approach is if it's magnetic noise, the instant we cut power, it goes away. That's a strong indicator. That's telling us we've got a magnetic noise source. If it's mechanical noise, when we cut the power, the noise greatly diminishes, but it'll tend to, it's like a coast down, like a kind of a rumble, if you will. And windage, as soon as you cut the power, the speed, the windage is going to drop off, exponentially reduce in magnitude as the speed goes down. So those are kind of the characteristics. That mechanical is more of a linear diminishing. The windage is kind of exponentially diminishing. And if it's magnetic, it's almost instantaneously diminishing noise levels.
Good. Howard wants to know, where does fluting come in here?
Okay, fluting would be a bearing noise that would occur. The fluting, what we call our picket fence type marks, it's ridges on the outer race of the bearing. So it's going to be a high frequency noise caused by the most common source that we see today for fluting is a motor that's operating on a variable frequency drive. And that's if we were doing something again like the bearing a fault analysis with a spectrum analyzer, or maybe even with ultrasound, we could detect that we've got a defect in the bearing. After it's taken apart, that's when the examination could reveal whether or not it was fluting that was the cause.
Good. What would be considered as not normal as far as motor noise is concerned?
Okay, in terms of the magnitude of the noise, there are, and I didn't go into this, but in NEMA, in Motor Generator Standards MG1, Section 9, there are tables which vary by the horsepower and the speed, number of poles of the motor, as to what's considered an acceptable limit for the dBA overall noise. So that information is available in NEMA MG1 Section 9. And if someone is interested in it and you don't have a copy of it, I'm not trying to advertise for NEMA, but they have, I would call it graciously in the last year, made MG1 available as a free download. So if you're curious about what's in MG1, you can download it. Like I say, in Section 9, there's a table that goes through for the motors. It also goes beyond the squirrel cage motors I'm talking about here, even at the DC machines, and what are the acceptable, upper limits on the noise.
Thank you. What is the best way to reduce motor noise when used with a VFD or variable frequency drive?
Okay, that in many cases, what I call is a double-edged sword. If we increase the carrier frequency of the drive, let's say it's at 8 kilohertz and we increase it to 20 kilohertz if that's possible, or 22 kilohertz, as we get it to the point where it's going beyond the range of human hearing, the audible noise that we hear from the drive is no longer, objectionable to our ears. But that chopping, what it's doing is taking DC and artificially chopping it into AC. Now we've got more chopping action that's trying to erode at the windings and at the bearings. So that's our trade-off, that the increased carrier frequency may make it sound less noisy, but it might become more damaging.
Well, thanks, Tom, for the great answers, and thanks for the great questions, which have continued to come in as Tom has been answering them, and those will be posted on the website. I'd also like to extend special thanks to our sponsors, Grundfos, Lenza, and SCW Eurodrive, for sponsoring today's event. Now that we're just about done, we'd like to hear how we did. The exit survey will pop up on your screen as soon as the webcast ends. Please take a moment to complete it, because we use this information to improve our webcast. Finally, on behalf of CFE Media and Technology, I'd like to thank you for attending. That concludes our webcast. Thank you, and we'll see you next time.